Okay, what is meant by the term effective nuclear charge and how is it calculated? Well, for effective nuclear charge, there is a formula, and we've already done a problem like this, but the effective nuclear charge, or ZF, is Z minus S, where Z is the number of protons in the nucleus, S is the number of core electrons, the ones that are not valence, the one on the inside. And so, basically it's telling you how many protons a valence electron can sense pulling on it. That's how it's calculated. How does the effective nuclear charge experienced by the valence electron of an atom vary going left or right across a period on the periodic table? Well, probably the easiest way to look at that, we're just going to make two comparisons. So let's look at, for example, let's compare like lithium and fluorine. Okay, so there are elements in the same period as we go across. I'll draw just a real quick Bohr model. So here's lithium in its nucleus, so it has 3 protons. First shell, it's got 2 electrons. The second shell, it's got 1 electron. Okay, but we know that it has 3 protons in the nucleus. Let's go over and we said fluorine, right? So fluorine over here has atomic number of 9, so 9 protons. So 9 protons in the nucleus. First energy level, it's got 2 electrons. The second energy level, it's going to have 7 electrons. 1, 2, 3, 4, 5, 6, 7. Okay? So this one is fluorine. Well, in looking at this, if I'm calculating the ZF, 3 protons minus 2 core electrons, this gives me a ZF of 1 plus, which means this electron feels 1 proton pulling on it. If we look at this example with fluorine, okay, just any one of these electrons, so the ZF of fluorine, we have a total of 9 protons. Notice there's still only 2 core electrons. So 7 minus 2 is going to be 7 plus. So each of these electrons feel the pull of 7 protons pulling them in. It's going to pull them in closer. It's going to pull them in tighter. Okay, circle the element that has the smaller radius. So the thing you need to remember, so if we look at atomic radius, that's just the size of an atom. Going down a group, they get bigger. Okay, and that makes sense. As I go down a group, you keep adding rings, adding energy levels. So atoms get bigger going down a group. Going across a period from left to right, they get smaller. Why? It's that thing with that effective nuclear charge. As these valence electrons sense more and more protons pulling them in, they get pulled closer, they get a smaller radius. So which one has a smaller radius out of these two? Well, sodium or lithium, it's going to be lithium, because lithium is further up the table. Lithium has 2 rings, where sodium has 3 rings. Okay, strontium or magnesium, it's going to be magnesium. Once again, magnesium has 2, strontium has 5 rings, so magnesium is smaller. Carbon or germanium, same thing. Carbon is smaller, it has 2 rings, germanium has 4. Selenium and oxygen, it's going to be oxygen. Oops, went the wrong way. It's going to be oxygen. Oxygen has 2 rings, selenium has 4, so oxygen is the smaller of those. For number 8, we just kind of explained the reasoning why. Larger as you go down because you're adding more rings, smaller going left to right because of that effective nuclear charge. The more protons, the larger centralized charge, pulling those valence electrons in there. Number 19, arrange these elements in increasing atomic size. So that means we're going from smallest to largest, okay? And so out of these, the smallest one should be chlorine, followed by sulfur, followed by aluminum, and the biggest one should be sodium, okay, because they're all elements of the same period. They're all elements of the 3rd period. Looking here, they're all right in this line, and so the biggest ones are over here, the smallest ones are over here, so that is the correct order. Is that a group trend or a period trend? They're elements of the same period. Okay, this one's a little different because we're looking at ions in this case, which is okay. Just remember, let's take a look at like magnesium here, for example. Okay, and I might just draw a couple of Bohr models real quick. So here's magnesium. Okay, first energy level, it's got 2 electrons. The second, it's got 8, so there's 10. Magnesium has an atomic number of 12, so it's got 2 more electrons. Okay, all right, so this is a magnesium atom. Well, when it forms a magnesium cation, it has this 2+ charge. These are the 2 that it loses. And so it literally goes to this. You have magnesium with its inner 2, and then it's got 8. Okay, well, it sheds that outer energy level. So this is the magnesium cation. So cations are smaller than their neutral atom. So which one has the larger radius? Definitely magnesium. Well, in looking at this next one, you can probably make a prediction. If cations are bigger than cations are smaller than their neutral atom, anions must be bigger. And that is indeed the case, and I'll tell you why here in a second. And so here's oxygen. I'm just going to draw one oxygen here. Here's oxygen. First energy level has 2. Normally it has 6 valence electrons. So this is elemental oxygen, looks like this. Well, when it becomes an oxide anion, it picks up a couple of electrons from something else. Okay? And so when it does that, you have to recognize that the protons don't change. Okay? The protons don't change, and also we don't add a ring, we don't remove a ring. It has the same number of rings. These electrons, you know, there's something we're going to learn here in the future called valence shell electron pair repulsion. As you squeeze more electrons in here, there's going to be more repulsion. They're going to pull slightly out. Likewise, I mean, the effective nuclear charge isn't really changing because we still have 8 protons in the nucleus, still have 2 core electrons. And so, yeah, this guy, the anions are going to be slightly larger. Hey, looking at the next one, phosphorus and sulfur, and these are both anions. And so you have phosphorus gaining 3 electrons, sulfur gaining 2 electrons. You're going to notice that both of these things, I went the wrong way, phosphorus and sulfur both have 3 energy levels. Okay, so the number of rings isn't going to change. Basically what we are interested in, and once again, is that effective nuclear charge. We're looking at the number of protons that are pulling those electrons in. Phosphorus has 15 protons. Sulfur has 16 protons. Well, what's going to be able to pull those electrons in a little bit closer, having 15 protons pulling on them or 16 protons, because they have the same number of valence electrons. They both have 18 electrons. So now we're just looking at that effective nuclear charge, or the number of protons that pull them in closer. 16 can pull in closer than 15, so that means sulfur is going to be smaller. The answer, the bigger one, is going to be phosphorus. Okay, circle the element has the greater first ionization energy. So you'll recall first ionization energy, we talked about this, is the energy required to remove a single electron from an atom. Okay, so how much energy it takes to strip one down. As you go down a group, it takes less energy to remove electrons. Why? Because you're getting further from the nucleus, so a further distance away, and you also have greater shielding from those core electrons. As you add rings, you get more and more stuff in between, more electron shielding. Going left to right, the first ionization energy is going to get bigger, so more energy. Why? And this should say energy, not electrons. Energy. Okay? So it takes more energy as you go across. Why? Well, once again, you're getting closer to that magic number. You're getting closer to the octet. You're also, you have a larger centralized positive charge. That ZF is getting bigger as you go across. So more protons, stronger pull. So in looking at these examples, which one would have the greater first ionization energy? So it increases as you go left, right. So there's sodium and aluminum. Definitely aluminum. Calcium and strontium. Okay, Here's calcium, here's strontium. Definitely calcium. Potassium and bromine. So here's potassium, here's bromine. Definitely going to be bromine. Oops, wrong way. Okay, explain why the ionization energy gets greater going across the period, smaller as you go down. We just kind of did that, didn't we? So we talked about as you go left to right, larger effective nuclear charge, so more protons pulling those electrons in. You're getting closer to an octet, takes more energy. As you go down a group from top to bottom, the valence electrons are further from the nucleus, more shielding from those core electrons. 23, arrange these elements in order of decreasing ionization energy. And so beryllium has the lowest, followed by magnesium, followed by calcium, followed by strontium. This is a group trend. Okay, so decreasing, yeah. So this is, or you know what? I should actually have these arrows drawn the other way, because this is less than. Yeah, less than points to the left. I was drawing greater. Oof. There you go. But that's the order. So that is decreasing ionization energy. This one is less than magnesium. Oh, you know what? Hold on a second here. I think I had those drawn the correct way. Decreasing. So the arrows were correct. I guess ignore what I was just doing. We're going from the greatest to the smallest. Yep, I was correct. Here I was confusing myself. I had the right order. I drew them right, and then I got second-guessing myself. Now, that should be those decreasing. So the greatest amount to the less amount. This is greater than this. This is greater than this. Yep, that's what it should be. Okay, in this example, we have 3 electron configurations and some first ionization energies. And so the easiest way to think about this, think about which electron would be the easiest to grab. Well, it would have very few valence electrons, and they would be furthest from the nucleus. So one of them, this one, is a 5s1. It's clear out in the 5th energy level. It's further than all the other ones, and there's only a single one. That's going to be the lowest amount of energy. So these two go together. Okay? And looking at the next two, one of them is definitely going to have the highest, because one of them has a completely filled octet. C does, because if you look at 4s2, 4p6, we're looking at the element krypton there. So it has a completely filled energy level. It's got a very high ZF, an effective nuclear charge of 8+. It's going to take the most energy. So these two should go together. And then the one that's left over is the other one.